Hello everyone, thank you for coming. My name is Federico Sejers, and today I will be presenting the work titled Consensus over Clustered Networks with Asynchronous Intercluster Communication. The consensus problem appears in many applications, such as in the rendezvous of mobile robots, attitude synchronization in satellites, and distributed ledger verification for blockchain applications. In all of these examples, we have a network of systems whose individual states are governed by some dynamical process, where it is the goal to drive all states into agreement. Consensus can also be applied to clustered networks. Here we present an example on the left. Suppose there is a team of satellites that is divided into groups, i.e. clusters, where each cluster orbits around the Earth. While the satellites in each cluster can continuously communicate with their neighbors that are in the same cluster, communication between clusters may only be intermittent. Next, we show an example of a clustered network on the right. Given a graph G, we can divide the vertex set into clusters, where the pieces of G that connect two clusters together define an intercluster. The cluster set script C defines the clustered network, which consists of strict subsets of the vertex set that are pairwise disjoint and whose union equals the vertex set. We now arrive at the problem formulation. Consider a multi-agent system composed of n agents that coordinate over an undirected graph G that consists of a fixed vertex set and a fixed edge set. The graph G is then partitioned according to some user-defined cluster set script C. Each agent in the network has a state variable that evolves according to the homogeneous linear time invariant dynamics presented below. Given these objects, the goal of this work is to develop a distributed controller for each agent so that the consensus error defined on the right is exponentially regulated through the use of continuous communication within clusters and both intermittent and asynchronous communication between clusters. The assumptions we make in this work are that each agent can measure their state at all times, the graph G is connected, and that there is at most one intercluster between a pair of clusters. To help us analyze this problem, we will employ the Goebel-Sanfelice-Thiel hybrid systems framework. Given M-star interclusters, intercluster R is assigned a timer, which evolves according to the following hybrid dynamics. One important thing I would like to make clear is that the graph G models the potential flow of information within the network, while the timer tau sub R determines when the agents of intercluster R can communicate with their neighbors in the same intercluster. The controller of agent I is designed as presented here, where the first term uses continuously available neighbor information from agents that are in the same cluster as agent I. The second term uses intermittently available neighbor information from agents in intercluster R as determined by the timer, tau sub R. So the first term is a traditional consensus term, where the edge weight aik is set equal to 1 if and only if edge ik is in the edge set. The second term in the controller evolves according to the hybrid system given here, where eta sub IR is held constant until timer R reaches 0, in which case eta sub IR is updated according to the traditional consensus update law. We now develop the hybrid system for the ensemble. Let E denote the stacked consensus errors for the multi-agent system. Eta denotes the stack of the control components that utilize the continuously available neighbor information. Theta sub R denotes the stack of the control components that use the intermittently available neighbor information from intercluster R. Theta denotes the stack of all the theta sub R's, and tau denotes the stack of all the timer variables for the M-star interclusters. The flow dynamics for the stacked consensus error are presented here. Since the consensus error E is continuous, the consensus error is mapped to itself during a jump. Given the hybrid model for eta I sub R on the previous slide, the flow and jump dynamics for theta sub R follow as shown here and here. While we could analyze this hybrid system, we will introduce a coordinate transformation as shown here to aid the analysis. The flow and jump dynamics of the coordinate transformation corresponding to intercluster R are presented here. Hence, the original hybrid system can be re-expressed using the coordinate transformation to obtain the following. One neat thing that I would like to point out is that even though we have partitioned our graph G, the Laplacian of G can be recovered. If we focus our attention on this term here, and we use the definitions provided in the paper, this term can be expanded as shown here, where we can see that the Laplacian appears right here. We now present the complete hybrid system. The variable z is defined as shown here. The flow set C is defined as the set script x. The flow map F is defined as shown here. The jump set D is presented here. Likewise, the jump map is shown here. Lastly, the consensus set is defined by script A, where our goal is to show that this set is globally exponentially stable. Before I present the main result, consider the following. Since the graph G is undirected, the Laplacian is symmetric. Moreover, since G is connected, then the smallest eigenvalue of L is 0, and all other eigenvalues are strictly positive. The symmetry of the Laplacian means we can diagonalize L to obtain an orthonormal basis for Rn. We then define the matrix psi, which consists of eigenvectors 2 through n, and is used in the development of a bilinear matrix inequality. We now arrive at the main result, which states the following. Suppose assumptions 1 through 3 are satisfied. Given positive T2 super R, 1 R for each intercluster, the set A is globally exponentially stable for the hybrid system H with data CF dg if there exists a positive scalar sigma, gain matrix K, and symmetric positive definite matrices P and Q sub R, 1 R for each intercluster, such that the following bilinear matrix inequality holds for all tau in the set script T. Note that in this paper, one can find a supporting proposition that states that the matrix inequality in the theorem can be relaxed to a finite number of matrix inequalities using a decomposition. A quick sketch of the proof is now presented. We begin by considering the following Lyapunov function, which can be bounded as shown here. During flows, the time derivative of the Lyapunov function can be expressed as shown here. Using the bilinear matrix inequality and the bounds in the Lyapunov function, we can upper bound the derivative of v as shown here. Note that zeta is a positive constant defined as the negative supremum of the maximum eigenvalues of the BMI, whose eigenvalues are all negative. During jumps, the change in the Lyapunov function is given by the value of v after the jump minus the value of v before the jump. Without loss of generality, suppose only intercluster Q exhibits a jump. Then, the change in the Lyapunov function can be expressed as shown here. Hence, the change in the Lyapunov function during jumps is non-increasing. Next, for each s and for almost all r in the closed interval from Ts to Ts plus 1, the solution phi of Rs can be shown to be in the flow set C, where the development on the previous slide can be used to obtain the following differential inequality. Integrating both sides yields the following. Similarly, using the development on the previous slide, we can obtain the following inequality. Putting these pieces together through a telescoping argument, we can obtain the following exponential bound for v, where, after some algebra, we can show the consensus set script A is globally exponentially stable. Now, we present some simulation results. The dynamics of each agent in the clustered multi-agent system are presented here with a prescribed gain matrix. Note that the gain matrix K satisfies the matrix inequality in the theorem previously presented. The timer parameters are presented next, where the agents in intercluster R can communicate as fast as every T1 super R time units and as slow as every T2 super R time units. Note that these parameters must be selected such that the Lyapunov function is non-increasing for all time. Also, whenever a timer reaches 0, the timer is randomly reset to a value within the closed interval from T1 super R to T2 super R. For simplicity, the dynamics of each agent in this example are those of a harmonic oscillator. A 16-agent multi-agent system is considered with the following network structure. The graph G is partitioned into 3 clusters and 2 interclusters. The clusters are color-coded, where clusters 1, 2, and 3 are depicted by the green, orange, and blue sets of nodes, respectively. Intercluster 1 is shown here, while intercluster 2 is shown here. Next, we show the simulation results, where the top plot shows the consensus error for all agents. Notice that all errors converge to 0. The middle plot shows the evolution of the timers for the 2 interclusters, where the intermittency and asynchrony in intercluster communication is illustrated by the different times that the timers reach 0. The bottom plot shows the value of the Lyapunov function. Notice that each time a timer reaches 0, i.e. an intercluster communication event occurs, the Lyapunov function jumps down while the consensus error temporarily increases. Because our hybrid system can be shown to satisfy the hybrid basic conditions, the proposed controller is robust to vanishing perturbations. To show this, we performed a second simulation with the exact same parameters, where we expose our agents to a sinusoidal disturbance in the state. Along each coordinate and for each agent, the magnitude of the disturbance is 0.01 and the phase is randomly selected from a uniform distribution on the closed interval from 0 to 1. Here we have the corresponding simulation. The top plot shows the consensus errors for all 16 agents which converge to a neighborhood of the origin with radius 2. The second plot shows the evolution of the timers for all interclusters like in the first simulation. So in conclusion, we have developed a controller capable of globally exponentially regulating the consensus error for a clustered multi-agent system whose agents continuously communicate with their neighbors in the same cluster and intermittently communicate with their neighbors in the same intercluster. We are also able to show that our controller is robust to vanishing perturbations. In the future, we can consider both intermittent and asynchronous communication within clusters. One way of expanding along this line would be to assign each agent a timer and attempt to reproduce a similar stability analysis. We may also consider more complex dynamics or even model uncertainty, where one could employ adaptive control techniques to estimate the uncertain model in addition to achieving the consensus objective. Another idea would be to consider event-based communication rather than the use of timers, where we may be able to ensure sufficient network connectivity through an event trigger mechanism. We can also consider systems with states that are partially observable and develop state observers to reconstruct each agent's state. Lastly, we can also attempt to enlarge the maximum allowable transmission interval so that our agents can go for longer periods of time without needing to communicate. This concludes the presentation. If anyone has any questions, I'd be happy to take them now. Thank you.